We know it has to be mediated by a carrier because these things are big and hydrophilic, so they can't pass through the phospholipid bilayer, right? So we have to help them across. If they're going from high concentration to low concentration, that's just termed facilitated diffusion. If they're going against the concentration gradient, which at some point they will, right? Because you want to absorb not just the equilibrium, but all of it, right? I don't want just 50% of the glucose I intake being absorbed and 50% being eliminated. I want all of it being absorbed. Right? So at some point you're going to have to go from facilitated diffusion with the concentration gradient driving the movement to active transport, and you need a source of energy. The energy could be ATP. We call that primary active transport. Or it could be co-transport with something else. Diffusion could provide the energy to do it. So here's a glucose transporter right here. This is a sodium glucose transporter. So guess what we call it? SGLT. Sodium glucose transporter. GL is glucose, S is sodium. So sodium glucose transporter. So this is co-transport. Sodium diffuses in. Glucose is actively transported in. This now, high concentration in here, low out here. Facilitated diffusion into the bloodstream. Okay. There are also transporters called just GLUTs. GLUTs stands for glucose transporter, and they actually can use ATP, although it's not shown here. They can use ATP to drive the movement. And these GLUT transporters have an affinity for both. Remember protein ligand interactions, right? So the transporter is the protein. It has an affinity for the ligand. The ligand in this case is the monosaccharide. It has a higher affinity for glucose than fructose, but it does have some affinity for fructose. So if they're both present, glucose and fructose, it would prefer to transport glucose because it's got the higher affinity. But if glucose is being actively removed by these other transporters, these will then have competition, right? There will be some availability of them to also transport fructose. But the point is this, right? Whether it is secondary active transport, primary active transport, or diffusion, we're moving into the epithelium, into the interstitial fluid, and into the blood capillary. As what? As monosaccharides. It has to be as a monosaccharide. And once they're in the bloodstream, of course, they then would go, right, that was a blood capillary. They would then go to the liver, and the liver, under certain conditions, right, if it has the right regulation, would be taking them out of the bloodstream and storing them. What's the liver going to store them is? Probably glycogen. It's probably going to take all those monosaccharides, convert them either into glucose if they weren't already, hook them together and store it as glycogen. There are two types of cells in the body that store a lot of glycogen. One of them are hepatocytes, that store a lot of glycogen. The other is muscle, skeletal muscle, because skeletal muscles need a ready supply of glucose. They don't want to have to wait for blood to continually bring more glucose in as they start working, right? So they store some. And that's logical, right? Because there are times when muscles have such a huge demand for nutrients, and that's when we're exercising or actively working those muscles, so they can store them.